Hi all, this is a quick attempt to try and show how I use the ArduCopter Analytic Tune Tool to tune an aircraft. This can be found in the web tools under the work in progress tools, and if you come down here to the Analytic Tune, this is put together by Bill Geyer. Come in here and you can choose a file, load it, and you'll get a list of all of the system ID runs that you've done in that flight, and you can see the axis of each sys ID. And you can see the first one I did, I actually aborted it and started again. Then you can choose one. We're going to look at roll here. You can see that there's of the sysID axis, there's an input roll angle and there's a recovery roll angle. Now, the way sysID works is it creates this chirp and it feeds it into various parts of the controller, of our controllers. And so the chirp is made up of a constant frequency where the magnitude increases to this value that you've set. Then it maintains a constant size as the frequency increases, and then once it gets to the top frequency it reduces down to 0 again and finishes. And so this tool will automatically select the full range, so it's using just the right data set for the data that for all the calculations that go on below. Once you've checked that, you can click calculate and you'll start to see these values here populate up, and with the tune that you've actually used. Now I'm going to reset this back to a conservative initial tune that you might get after you've done a test flight and you've got something that's stable, but stable enough to fly, but conservatively stable. If you'd run auto tune, you might be closer to your perfect tune, or you might be slightly over tuned. But either way, you can actually back this off below your tune to go through this process just as I've done here. So the first thing I do is not to actually start tuning this. It's actually to look for saturation. Like all of our tuning mechanisms, the maths assumes a linear system. So it's really important to avoid saturation and non-linearities. So like everything else, having your expo set correctly will ensure that you get the same gains at low throttle and high throttle. Ensuring that you aren't clipping will ensure that the data you collect isn't distorted where you start to see that clipping. And so just opening this up here and having a quick look here, these are the two roll auto tunes. Now this one here is the one we're looking at, the input roll angle, and the second one is the recovery roll angle. Now the recovery roll angle feeds that chirp in directly into the attitude target and turns off the command model, which means that it has the high frequency response is greater. So it's good if you actually want to get some more power in the high frequency response. But you can see here that the rate output's actually increased above the throttle level, and this will mean we'll start to get saturation. And you can actually see here that during this system ID I had to reduce the throttle slightly to stop it climbing. And so this isn't what you want to see. Anytime you see this, you're going to want to reduce your maximum lean angle to ensure this doesn't happen. So to do it with the recovery roll, I'll probably need about half what I've asked for here, because you can see the input roll has that it goes through the command model, and that smooths everything out a little bit, and reduces the magnitude of the frequency response, especially at the higher frequencies. So you see down at the lower end it looks reasonably similar, slightly less, but then at the high end the acceleration limiting and all that sort of stuff really limits it. But things like acceleration limits, that sort of stuff, do tend to be nonlinear things, so that too can be non-ideal. My personal preference is to use the recovery roll angle, but to keep the magnitude such that this doesn't happen. But for this example, we're going to look at this because it's not saturated at all. So, okay, so what's the first thing we want to look at here? So, like just when we're doing a manual tune, the first step is to tune up the rate PIDs. And so if I have a look at that, we want to look at the rate controller. Now, when we, you'll start out with it all set to maximum like this. So if we, so what this is telling us is 0 dB is 1. If this orange line sits on the 0 dB, it means we're getting the same magnitude out that we're asking for. And this phase here gives us an idea how far behind what we ask for what we're seeing, the output is. So you can see at low frequencies, our gain's close to 1, close to 0 dB or 1, and we've got a very small phase. So it's there, it's slightly behind, but it's there. As we go to higher and higher frequencies, the output gets smaller and smaller, but also it falls further and further behind the command. So this is basically like putting a sinusoidal input into your sticks and going faster and faster and faster. And one of the key points you want to look at here is 6 dB is where the output is half the size as the command. Okay, so at about 6.25 hertz, 6.256 hertz, we have about half the output magnitude, but at 6.25 we're about 160 degrees behind. So we're going to see if we can improve this, and you can see the blue line is actually from the original starting tune, so we're probably going to end up moving closer to that, but I'll show you the process with which I use to find that blue line. So the first thing I'm going to do is I'm going to turn off the iTerm, and you can see that drops down this the low frequency end. Now what we want to do is we want to increase. I'm going to actually zoom in here so we got a little bit better resolution. So we want to bring this up closer to the 0 dB line where the output's the same as the input. Okay, now here we've gone above it though, so we don't want to do that, so let's just back that off. So now we're not overshooting, we're not getting greater than what we asked for, but it's up pretty close to it. So now we can start increasing the D term. Now as we increase the D term, or the dampening term, you can see the low frequency terms actually slow down, but the higher frequency terms are coming up. And you can see now as we get up here, we start to actually get these higher frequencies. We're starting to get higher oscillation, like we're actually getting these higher frequencies. The outputs are becoming larger than what we're asking for. Now the key thing we want to do here is we also want to look at where the output is 180 degrees out of phase to what we're commanding. So basically, when you're rolling left, right, left, it's going right, left, right. It's going in the opposite direction in perfect time with your commanded inputs. And so my rule of thumb there is that I don't want at the 180 degree point, you can see that where it flicks low to high, I don't want that to be greater than 3 dB above the command. Sorry, I want it to be half, so minus 3 dB relative to my command. So this is minus 3 dB here, so I want all of this orange to be below, or you know, there's a bit of noise here, but I want that orange to drop below that input there. So we're getting down to there's a bit of noise, but we're getting down clearly below that. All right, now, okay, so our angle P, we've taken this up close to 1 now. Now, in order to get maximum stability, so if it was right on 0 dB, it would be critically damped. We want it to be slightly under damped. So that means we're just focusing a little bit more on the reaction to that input. And that's where we tend to get our best balance. And my rule of thumb here is to bring this maximum here just up to the 1 dB point. So if I increase that up, that's a little bit, yeah, so it's just, yeah, I can't go any further than that. And you can see here that the D term, let's check that again. So we're looking around the 7.23, 7.32 hertz. Yeah, perhaps a little bit lower on the D term, drop that down a little bit. So you can see we're sort of dropping past the 3 dB, and this is just scraped past the 1 dB, bit of noise, hard to see exactly where it is. And so that's going to be my P and D terms. And then I'm simply going to set my I term back to, to what my P term is. Now, and you can see that that made this jump up. And you can see that if I reduce that, the low frequency drops down. And if I increase that, I start to get a larger response on my low frequency stuff. So this the one-to-one ratio will tend to work well on most aircraft. Some bigger aircraft may need the I term a little lower to prevent overshoot, and some small aircraft can tolerate a higher I term. So I'm going to call this good on my rate loop. Now the next thing I need to do is I need to tune the attitude loop. Okay, so here we can go down to the attitude controller without feed forward. And this is the, with feed forward, you're basically flying, the controller's basically flying in acro mode, and then just compensating for any attitude error. When we go without feed forward, we're actually flying the aircraft directly through the attitude controller. So we're exercising that angle P term. So let's just reset this graph. And you can see here, again, we want the angle we ask for to be the same as the angle we get. So that's going to be that 0 dB line, which is there. So let's start by increasing the angle P to bring that up. Okay, that's coming up now. Okay, that's looking pretty good. And now we're starting to run along that 0 dB line and drop off. So let's just come in there and have a closer look at that. Now, the control, the parameters itself only start at half a hertz. So we don't. The sweep only starts at half a hertz. So anything below this sort of 1 to half a hertz is sort of bad data. Like once you get below half a hertz, there is no data, and the results are really just looking at the rest of the aircraft while it's actually hovering there and picking out some data. But you'll generally find you're only interested from across the range that you actually set, and that's perhaps one of the things we might do on this tool is actually make it automatically limit the graphs to the range of the system ID. But as we go through here, you can see we're just starting to peak over 0 dB. And initially you might go, oh, that's really good. Okay, so 10, that's it. But no, we also have to have a look at the phase. And you can see that about 4.1 hertz, the angle is going to be in the opposite direction to our request. It'll be here 4.1 hertz. It's a little low, but a little lower, so it's not going to be as big, but it's moving in the opposite direction. So when we're going right, left, right, left, right, left, it's going left, right, left, right, left, right at that frequency. So my rule of thumb here is that I want this 180 degree crossing point in the magnitude to be 6 dB down. So if I just reduce that down, so I want that, this is the 6 dB line here, so I want to reduce that down to 6 dB. So that's basically half the size, okay? So you can see now that 4.1, 4.2, it's 6 dB down where we get the 180 degree phase change. And so that's coming out at 7.9. So and that is pretty much my process at finding a decent tune. You could potentially, I wouldn't go any, I would do it at least 3 dB down, so at least past minus 3 dB. So if we just said minus 3 dB, it's going to be approximately there, maybe just a little bit higher. Yeah, so that's the minus 3 dB there. So you can see it was only went from 9.9 down to 7.9. So it doesn't take too much to get that extra 3 dB. But AutoTune, I think, gave me closer to 9 when I did AutoTune on this. And 10 felt stable, but it just felt like it was just a little bit too reactive, and I ended up, when I did this manually, I ended up with a value of 7 as I backed it off. And you can see at 7, 4.1, I'm like an extra dB and a half below that minus 6 point. So that is my tuning process. Now the other thing we can look at rate loop stability, which I find quite interesting. So you can see here that at 6.45 hertz, 180 degrees, it's about here, it's very close to that 6 dB point, which is quite interesting. The 0 dB gain, it's minus 123. So the phase margin, 60 plus degrees there. Gain margin, 6 dB. So if we have a look at attitude stability, we're getting, it's about I find it tends to come out about the 9 dB. And then once you get the entire system stability, it's about the 6 dB again. So yeah, that's my process. That's how I run through this tune. Now if I actually bring up, so my initial starting tune, you can see here that I'm almost spot on. So this was 1.4, so very close, and my roll angle P was 7. So if we have a look at the rate controller, so and you can see that when you have the same tune that the SysID was flown on, these graphs tend to match up well. All right then. Well, I hope that's a good introduction to how I currently use this tool to tune. I've tested this on a 75 kilo, a 50 kilo, a 25 kilo, a couple of 10 kilo aircraft, and a little 5-inch quad as well. I have looked at other people's data, and I do occasionally see some of the data does look strange, and this process doesn't seem to work, but that may be caused by this saturation. You know, I don't think I necessarily examined the log to see if there was any saturation for those aircraft, but it may also have been caused by any number of other non-linearities, Mott Expo not being set correctly, output saturation, cell limiting, yeah, any of those other elements too may have caused that problem. All right, guys. Well, I hope everybody finds that useful, and I look forward to talking to people on the forums about this, and I hope this tool starts becoming more and more used, and our understanding of how best to use it improves. I'm sure Bill will have a lot of input into this as well. Helicopters again rely heavily on the feed forward, so that's a little that's requires some other steps as well. And of course, all of these filter settings also impact this tune, and you can look, for example, about how reducing the D filter settings actually allows you to push D term up further, for example, by making the control loops faster. What this doesn't show, though, is the impact of noise through the system. So my general process is to set all of the filter settings with I tune up the aircraft, set all the filter settings so I've got an acceptable levels of noise, and then run through this process knowing that I can't reduce my filtering any further without compromising the noise performance of my aircraft. So yeah, okay, thank you very much, and I'm sure I'll talk to people on the forums about this soon.